This is a hard disk drive. We're going to look at the two fluid mechanical components here, the air filter and the head. The head is a very interesting fluid mechanical system because it needs to be kept off the disk to prevent crashing. It's done by slightly angling the head, which creates a pressure which lifts it off the disk. We're going to look at that in our video. So starting with the air filter, we have our disk spinning at 7,200 RPM. We can draw a streamline around this air filter cavity. If we look at the elevation chart, we see that the elevation goes down, which means a much larger cross-sectional area, finds the filter, and then goes up again. And what we see with the pressure chart is as our area increases, speed decreases, so our dynamic pressure turns into static pressure, and then it has the exact opposite effect on the uphill. You might notice that there's a pressure drop right over the filter, and that's what's required to push air through the filter. If the uphill isn't here, our elevation stays down here, and our pressure stays up here, and there's no drop to force the air through the filter, and that's why the uphill's there.
In examining the flow in the hard disk drive, we're going to be looking at these two flows, and the way we get these two flows is by starting with a Navier-Stokes equation. And for conservation of momentum, we're looking for steady solutions, so we know that the derivative of u with respect to t is 0. And for the convective flux of momentum, we know that the derivative, we know that the x, the two solutions we're looking at have that the x component is 0, and the y component we know is going to be 0 because the height is very small compared to the length along which the flow is occurring, and the z component is also 0 because we're considering an area average flow. Now, on the right-hand side of the equation, we have the gradient of the pressure, and we assume that pressure is a function of x, so this simplifies to be pdx. And for the viscous forces, we have that the velocity is a function of y, and it's in the x direction, so this again simplifies to a single scalar term. Now, for the first flow, which is a couette flow with the bottom plate being driven at a velocity of u, we have a linear velocity profile and a constant pressure, so a pressure gradient of 0. The volumetric flow rate in this case is u times a over 2 because the average velocity is simply half of u. On the second example of flow we'll be considering is where there is a pressure gradient and the velocity is 0 at the top and the bottom. So because this pressure gradient is negative, the flow will be going to the right, and it has a parabolic velocity profile maximized at the center, and this also has a volumetric flow rate, and this volumetric flow rate expression is proportional to WH cubed, and it's also proportional to the magnitude of the pressure gradient.
All right, so moving forward with our analysis, continue to look at a couette flow, but now we're looking at an angled kind of slope here. And basically what you can see is that you'd have an initial height towards the front that's greater than the height later on. And what this changes is the cross-sectional area. So now you have a smaller cross-sectional area, but we're assuming that it's still a constant velocity throughout, that the velocity changes very minimally. So now you have a mass flow rate at the front that's greater than the mass flow rate later on. And kind of this creates is it's no longer satisfying the conservation of mass, which is this horizontal relationship between the mass flow rate and the distance here. And kind of what we need to do is create or add in a solution here that will counter this from our analysis, and that can be done by adding a pressure-driven flow. And we know that the pressure gradient is inversely proportional to the volumetric flow rate, and so as we can see here, and based off of our pressure gradient slope, we can see it's linear, and that goes to a quadratic relation between the pressure. And kind of this is what we want because it'll create a pressure difference that's positive, lifting the arm up from the disc to ensure that it doesn't crash.
So now we're going to look again at the Navier-Stokes equation and look at how our assumptions have changed. So for these flows that we looked at here, we said that du dx was 0. And in this case, we just found that du dx cannot be 0. It has to change over x because area is changing over x. However, we're still going to consider that term to be negligible because it's so much smaller, the change in speed is so much smaller than the viscous effects here. So in this case, we are still maintaining that this is a steady flow. We're maintaining that the speed does not change in a significant way in any direction, and that the pressure gradient is in the x direction as well as the velocity in the x direction.